Here's what we know so far. We know that protons determine an atom's identity. We know that electrons determine an atom's charge. And we know that neutrons determine an atom's stability. Should have this table in your notes now. Proton is the same as the atomic number. It's the top number on the periodic table. The electron is the same quantity as the proton. So again, it's the top number on the periodic table. And if you figure out the number of neutrons off the periodic table, you take the atomic mass, which is the bottom number, you round that off, and you subtract off the top number, the atomic number, and that will give you the number of neutrons. We know that the charge on a proton is positive, the charge on an electron is negative, and a neutron is neutral. The proton and the neutron are both found in the nucleus, and the electron is found outside of the nucleus. And then we talked about the mass of the proton, electron, and neutron. The mass of the proton and neutron we said were 1 AMU and that the electron was 0.005 AMU. And the question came up, well, what's an AMU? An AMU is an atomic mass unit. So learning target number 3 is to know that AMU stands for atomic mass unit. That's what it stands for, but that doesn't really tell us what it means. So when AMU is defined as exactly 1/12 of the mass of a carbon atom with a mass number of 12, which again doesn't mean a whole lot to us yet because we don't really know what a mass number of 12 means. So we need to explain what that means. Now if you want to convert AMUs into kilograms, and we never will, but if you wanted to, you could see that it's a really tiny number. So protons and electrons and neutrons are teeny tiny. Out of those three, the electron would be the smallest of the three. So here's a question. If protons and neutrons are each 1 AMU, how do we get atomic masses listed on the periodic table that are not whole numbers? For example, carbon's mass is listed at 12.011 AMU. Now, even if we include electrons in the mass of the atom, which we never do because it's such a small number that it doesn't affect the mass at all. But even if we did include them, it's not going to add up to 0.011 AMU. So how do we get that decimal if it's not from the electrons? And the answer has to do with isotopes. So we need to define what an isotope is, learning target number 4. Isotopes are atoms with an identical number of protons but different number of neutrons. Now the periodic table shows normal atoms, most common atoms. Any atom of that element that has more or less neutrons than normal is an isotope of the normal atom. The term isotope is often just associated with the atom that has the abnormal number of neutrons, but both are technically isotopes of each other. So, going back to atomic mass and how we get that 12.011. The atomic mass is the weighted average of all of the different isotopes. So the more commonly found isotopes are going to have a greater effect on the average. Here's an example. If I took a sample of carbon, most of the atoms of carbon are going to be 6 protons and 6 neutrons. But every once in a while you're going to find one atom that has an extra neutron. Now when you take an average of these atoms, you're no longer going to get a whole number. And if you include the most common isotope of carbon that has 6 protons and 8 neutrons, it's going to change that average even more. So again, when you take the average, the more commonly found isotopes are going to have a greater effect on that average. So the 6 proton, 8 neutron isotope is going to have more of an effect on the average mass than the 6 proton, 7 neutron isotope will. So learning target number 5 is to know that the atomic mass is a weighted average of all the isotopes of an element, and that's how we get the decimal on the periodic table. You'd never find an atom that has that particular mass. That is an average out of all of the different atoms that would compose a sample of that particular element. Now we express isotopes using what we call symbolic notation. It looks something like this. The 6 is the atomic number, and the 12 is the atomic mass number. Now they're opposite what you'd see on our periodic table. On our periodic table, the atomic number is on the top, and the atomic mass is on the bottom. Here we flip-flop the two. The 6 is on the bottom now, and the atomic mass number is on the top. And that's the other difference. It is an atomic mass number, not the atomic mass. You notice it doesn't have the decimal points. It just has the number 12. The atomic mass number represents the total number of protons and neutrons in that particular atom. It's not an average, it's the number in this particular atom. The atomic mass, again, was the weighted average of many different atoms. This is the mass of a single particular atom. Now that's the normal carbon, 6 protons and 6 neutrons for an atomic mass number of 12. This one would be an isotope of carbon, and it has, again, 6 protons because it's still carbon. But now it's telling you that there are 14 total particles in the nucleus. 6 of them are protons, the other 8 must be neutrons. Okay, so think of the atomic mass number like the total number of people in the room. The atomic number is the number of females. The difference then is the number of males. So if I have 12 people in this room and I know that 6 of them are female, I can figure out the number of males, or the number of neutrons. That would be 6. In this particular room, there are 14 people. If 6 of them are female, the difference between them must be the males. So if I take 14 minus 6, I'm going to be left with 8 males, or 8 neutrons. The other way that we can refer to isotopes is using an isotope name. To name isotopes, we just use the element symbol, a dash, and then the atomic mass number. Sometimes we'll use the entire element name instead of the symbol, followed by the dash and then the atomic mass number. So it'll look something like this. For carbon, normal carbon atom, it's going to be C-12 or carbon-12. 12 total particles, 6 protons and 6 neutrons. You don't really need to know that it's 6 protons because if you look it up on the periodic table, anything with carbon is going to have 6 protons. In this example, C-14 or carbon-14, it's telling you that there are 14 total particles in the nucleus. You need to know that carbon always has 6 protons, so again, if you do the math, that leaves 8 neutrons. Learning target number 6 is to know that elements on a periodic table can have isotopes that are either stable or unstable. We'll talk more about this in our nuclear unit. So some isotopes are stable, other isotopes are unstable. To make things easy on us, we are going to assume that any atom with an abnormal number of neutrons is unstable. Now that's not always true. When you get into chemistry or you get into nuclear physics, you're going to learn more about which isotopes are stable or unstable. But to make things easy, we're just going to make the assumption that any atom with an abnormal number of neutrons is unstable, and anything with the normal number of neutrons, like shown on our periodic table, is going to be considered stable. So here's a little bit of practice. If I gave you this particular diagram with the black dots representing protons, the white dots representing neutrons, and the tiny gray dots representing electrons, I'd like to know what the atom's atomic number would be for this diagram. So to answer that, you'd count up the number of black dots, 1, 2, 3, 4, 5, and that means it has an atomic number of 5, since the atomic number is the same as the number of protons. In this diagram, the atom's atomic mass number would be the total number of particles in the nucleus. So if I count up the 5 protons, add in the 1, 2, 3, 4, 5, 6, 7 neutrons, that gives me a total number of particles in the nucleus of 12. So the atomic mass number would be 12. The name for this atom, including the dash, is going to be based on, again, the number of protons, 5 protons means that it is boron, and the dash is going to be the total number of particles in the nucleus, or the atomic mass number of 12. So this would be boron dash 12. The symbolic notation for this, we're going to replace the word boron with the symbol B, and we're going to put the atomic number down on the bottom, the 5, and the atomic mass number up on top, the 12. Last question I'm going to ask on a diagram like this is whether it's stable or not. And to determine whether it's stable or not, you need to determine if it has the normal number of neutrons or not. In this particular case, it has 7 neutrons. That's not normal for boron. Boron normally has 6 neutrons, so since it's abnormal number of neutrons, it is going to be considered unstable in our class. So boron 11 would be the normal and stable one. Boron 12 would be unstable.